Suchetha Cooray telling us about learning from the color distribution of local galaxies. Welcome.
Am I picking up my voice? All good? Okay. All right, so thank you. I'm going to be another person who is going to change the title. Yeah, and I'm really shooting myself in the foot by giving an even more generic title, right? And am I going to make another joke? Yes. I'm not related to Suchetha Cooray, unfortunately. My name is Suchetha Cooray, and these are my collaborators for this work. And so I'm also part of the Universe Machine universe. And so some of my talk, part of the talk, is part of the. All right. So I'm gonna. So the talk I will be giving is a lot of the work that is ongoing, very preliminary, and basically the goal of this talk will be to just convince you that the work I'm doing is not really stupid and it really makes sense, and that why you should be really excited about what's coming up in the next couple of years. So empirical models. So we've had talks of empirical models, but I'm just going to give you another way to think about empirical models. So we've had ideas thrown around of different galaxy formation models that can be for different parts of the parameter space. So again, if you think of galaxy formation as in a statistical sense, we have this huge parameter space that we need to explore. And we need to constrain these from observations. And so you have your favorite galaxy formation models in different parts of, covering different parts of the model space, parameter space. One of them that we had discussed the first 2 days was how do you match high Z luminosity functions, UV luminosity. And it is as if taking a projection of this parameter space, projecting it down to these high Z luminosity functions, and comparing how do we match these different physically motivated models in this space. And what came out, rightly so, in the discussion session on the second day, is that the truth lies somewhere in the middle. So most of these models, physically motivated models, are not mutually exclusive, and the truth should be somewhere in the middle. And so the goal of empirical models, essentially flexible models, is to try and cover this whole space, so that we can be, in a way, statistically principled and be more conservative in our claims, and say that while we are testing this a more flexible, a wider parameter space, and this is what observations tells us. Often empirical models are also connected to this forward models approach. We've heard a couple of talks here yesterday in the Galaxy Halo connection of why we do full forward modeling and the benefits of it. And so the idea is, which projection should we take? So if we are comparing UV luminosity functions, it's great. But now when we look at another observable, now things are not matching. Now, what we can do with these empirical models, and if we can full forward model, we can start to answer all of these things sort of at the same time. But again, the problem is, what projection should we take? And what is your favorite projection, favorite observables? And I think the best projection we should take is the direct observables. What do we observe? And we should probably match those things. And the reason for doing that is we have a better understanding of our systematics, uncertainties, and also selections, right? And cosmologists have already figured this out, definitely. And so these people have been going to what they call them as field level inference. Essentially, in this case, this is clustering. Let's not limit to 2-point clustering. Let's go to endpoint and just do field level, right? And this is a constraint simulations in the cosmos field, basically getting initial conditions, running hydro, and comparing Lyman alpha tomography and such. But basically, what I'm trying to say is we need an empirical model that is full forward model, that is a full forward model. So just repeating what I've said, we need a model that satisfies most direct observations, modeling, and then we want to derive for parameter posteriors. Oops. Yeah, so since we are in a galaxy evolution workshop, I think I won't offend many people by saying we can assume cosmology as better than we assume galaxy formation. So how we do that is, first we assume a cosmology, start with a distribution of dark matter halos. Obviously, Phil might have problems with that, but the issue is we can start from these dark matter distributions and try to match galaxy observations, and do that in a forward model. So the connecting galaxies and halos come in a spectrum. Different people can have different opinions on where you should lie. In this case, we are falling right in the middle with empirical forward models. So the famous one of these empirical models is universe machine. I'm sure most of you are familiar with this, but the core of it is you are populating star formation rates into these subhalos, and then you calculate stellar masses by self-consistency modeling through the merger system, right? And how do you constrain this star formation rate function? Is you match these observations, like the stellar mass function, rates, correlation functions, and so on. And so it works well. It's been great. It's been very successful. But I'm going to convince you that we need a new version. And the reason is that these are matched to summary statistics. Summary statistics like stellar mass function, cosmic star formation rate, and so on. And this is because all these summary statistics come with a lot of uncertainties built into them. So when you think of SAD models, the question is how much information is there in a given SAD to derive your properties. Now, what happens is if there is no information, often your estimates of your properties are prior dominated. And these can then propagate towards your stellar mass functions and cosmic star formation rate and so on. And your predictions or inference of your galaxy formation model will also be biased. So this is a very interesting point, that even for redshift 0 galaxies, you have up to 0.3 dex, 3.5 dex, of uncertainties that come from modeling assumptions in your SADs. Now, an answer to that is, why don't we do it at a population level? From an individual galaxy point of view, we might not have enough information and therefore be prior dominated. But if you take the population and do a population level SED inference, then you have more constraints in the sense of a hierarchical. And so you can try to address some of these uncertainties by doing a hierarchical population level SED. And so how do we do that in the framework of universe machine is, well, you have these SFRs, you add dust and metallicity into it, then you get SED that you can calculate for each halo. And then now you constrain with observations, and these observations now are distributions of SEDs, luminosity functions, and correlation functions. So there have been very recent works that does this population level analysis called PopCosmos and PopSED. The difference between their work and ours is that we have additional information coming in from structure formation. So how do we do it? Take star formation machine, model dust and metallicity, or model, and then match the observed distributions of magnitude, colors and color magnitude. Now, this is tricky business because you are matching two distributions. So we are calculating a Wasserstein distance, essentially, which is not good. Yeah, we are able to do it. Very preliminary results. These are colors of SPSS bands that we are matching right now. Things are looking good. We use the shallow and fall two-component model, so we have planes for optical birth cloud and diffuse medium. Curves, I'll skip through. So what we've been doing is now match essentially the colors of these galaxies with redshift into a self-consistent model, but we observe images, right? So how do we go from SEDs, odd modeling up to SEDs, to now odd modeling to images? And that's where I think we can use some machine learning techniques like generative models. So these are some of 4 types of generative models. I've done all of them. But essentially what it means is you can get conditional information coming from an empirical model, use these generators to generate images. This is one example of it. So these are fake SDSS images, by the way. So this function of stellar mass and SFR, you can see that these are doing well. Now you put all of that together, coming from, well, essentially from cosmological parameters, running a dark matter simulation, populating galaxies, calculating SEDs, and SEDs with galaxy images. And you put them all together, and we can start making these fields of galaxies. I'm not claiming this is realistic. There are a lot of problems in there, but there'll be, we will try to solve one by one over the coming years. All right. I'm going to be controversial. Last slide, just because why not? Path to us being replaced. So if we can have a forward model, which is a big if, then what we can do is we can really quantify where we don't know in our galaxy formation parameter space. And that means we can calculate a loss function, essentially, to derive which observables need to be observed in order to reduce these uncertainties. And then that can predict, because we have a forward model, we can predict our survey strategies and designs for existing surveys or future surveys. And that means live updates, and these models can basically iterate themselves, and our job is done. All right, thanks.
Hey, beautiful work. Going back to this thing, I think the big if is the first one.
Yep.
Because this assumes that you know the parameters that you want to look for, or the main parameters that regulate galaxy evolution, which I think we don't know.
Mm-hmm.
So how do you see that in terms of, because if the set of parameters of the first assumptions are just wrong because you miss one of the main parameters, then all your optimization loop is essentially biased, right?
So of course there is going to be some physical assumptions that need to go through, but the point is, we do know to a certain extent what are the most important properties. If we are considering about certain observers, right? Let's say star formation rate and stellar masses, I think we are sort of good. But if you're talking about gas, I don't know. So I guess the point is, it also it really depends on which observers you match. And I think it's an iterative process. I don't have a clear answer, but.
Right. Thanks, Suchetha, again.
Thank you.